Swayam Prabha. Digital India. Educated India.
Welcome back. So, let me remind you that we were discussing in earlier class the feed tracks, and we said that feed tracks are normally connect the ball feeder with the assembly machine. This is because the ball feeders cannot be located very close to the machine, assembly machine, and therefore, there has to be a track. Now, while designing the part feeders, we said that the part feeders should be designed in such a way, so that inside the part feeder, the parts which are going in a right orientation should not be reoriented and lose their orientation, I mean. Now, we have shown some of the part feeders for feed tracks. So, these kind of feed tracks, for example, you have seen that this is for cylindrical part, for flat parts, for parts headed parts which are hanging in the slot. On then we said that the part feeders feed tracks are normally of two types. They can be of the vertical delivery of the parts, where the parts are fed with the gravity, and in that case that the time taken for a part to fall will be equal to 2 L by G root over, because this is the acceleration due to gravity that we are using to deliver the parts. Now, in the horizontal delivery of parts, section will be horizontal. For example, here this section and this section, these are horizontal. However, this part is actually not horizontal, but these are called the horizontal delivery of parts. Okay. Now, let us have an analysis of the horizontal delivery feed tracks, and let us see how the horizontal delivery feed tracks are designed. Okay. Let us take an example that this is the feed track that we have, and here we have the inclined portion, inclined straight portion, we have the curved portion, and then there is a straight portion. Okay. So, A B, this is the straight horizontal portion of the feed track. This is the curved, BC is the curved portion of the feed track, and CD is the straight inclined portion of the feed track. So, in here what happens, that this inclined one is inclined to this by an angle, let us say alpha. Okay. This angle is alpha. And this track is, let us assume that this track is filled with the parts. Okay. And after this, the parts are coming from the feeder from this side, and it will go through the feed track and it will be delivered to the workhead at this after A. This is the escapement of the parts. Now, it is assumed in the following analysis that a certain fixed number of parts are maintained in the track above the delivery point. Okay. So, let us assume that this feed track is filled up with the parts. Now, if the length of the straight inclined portion of the track containing parts is denoted by L2, this is the L2, and the length of the straight part is L1, okay, and the curved portion has a radius of r, okay, and this angle is alpha, that is starting of the curved portion and the end of the curved portion. So, in that case, the number of parts N p, total number of parts N p in the whole sector on the whole of the feed track, entire feed track from here to here, this will be equal to L2 plus r into alpha plus L1 divided by capital L. L2 here, L2 is here, this is the length, plus r into alpha here, plus L1 okay, divided by the length of the part like this. Now, the weight of the section AB, weight of the section AB here, this is equal to M1, L1 and the G. Now, M1 is the mass of the feed track with the parts. Okay. So, that is M1 let us say, and L1 is the length of the straight portion of the feed track into G. G is the acceleration due to gravity. The total frictional resistance in this region will be mu d M1, L1 and the G. So, what exactly that you understand, that suppose we have this portion, this is AB. So, this straight AB portion, okay, let us say this is A and B, this will have the M1 G, and this way, that is what we are showing here, that M1, L1 and the G, because this is L1. So, L, okay, and here it will be mu d M1 G L, that is what we are showing it here, M1, L1 and the G into the mu d. So, the mu d is the coefficient of friction, this is the dynamic coefficient of friction between the parts and the track. All right. The equation of motion for section AB therefore, will be given as F1 minus mu d M1 L1 G is equal to M1 L1 and the acceleration. This is A is the initial acceleration of all the parts. Okay. Let me going ahead show you this, that here in this AB we have this F1 if it is a free body diagram of the entire feed track. So, AB which is the straight part of length L1, this has then F1 here and F1 reaction here. Okay. So, therefore, if we have this M1 G and the L, so then this force which is going against that, it will be mu d M1 G and the L. So, therefore, the equation will be F1 and opposite direction is mu d M1 and the G L, mu d M1 L1 and the G. This is equal to acceleration, initial acceleration M1 into L1. So, this is the Newton's law that we are writing, that F1 minus mu d M1 L1 G is equal to M1 L1 and the acceleration. So, from here we can get it rearranging that F1, this is equal to M1 L1 is common, and this is mu d G plus acceleration, initial acceleration. So, what we have seen is that in the straight path, okay, in the straight path we have this equation of motion that can be actually written. Okay. Similarly, we can find out that how this inclined section equation can be made. So, here this is the inclined section is this one. Okay. Here we have the F2 and F2 here if it was F1. Now, what is F1? Let us say F1 is the force by the remaining of the parts to the parts which are located at the AB, okay, and the reaction will be F1 here. So, similarly, F2 is the force imparted on the parts located here by the parts located at the sector CD. So, therefore, what we can find out from here is that if it is L2, as we said, the distance is the length is L2. So, this is F2 which is force, reaction force coming here. Here it will be M1 L2 and the G like it was for the straight portion, okay. Like here we are having M1 L2 and the G. So, this force can be resolved into the perpendicular to the axis of this sector and parallel to the axis of this sector. So, here it will be M1 L2 G and the cos alpha. This force will be M1 L2 G and the sin alpha. Then there will be a friction force, okay, and that will be opposite to this, that will be M1 L2 mu d G and the cos alpha, and mu d is the dynamic coefficient of friction between the part and the track, feed track. So, therefore, from this diagram we can find out that F 2, that the equation of motion, that is F 2 is this opposite direction is m 1 L 2 g and the sin alpha, this one. Okay. And then there is one more which is along the F 2, which is m 1 L 2 mu d and the cos alpha, g cos alpha, this one. So, F 2 and these two forces have the same direction. So, these are in the plus, and the opposite direction is m 1 L 2 g sin alpha. So, this one, this they will be equal to the m 1 L 2 and the acceleration. Okay. This can be rearranged by F 2 is equal to m 1 L 2 common g sin alpha minus mu d and the g cos alpha plus a, because m 1 L 2 is common. So, we have two equations, one is for the straight sector and another is for the straight inclined at an angle with the horizontal by an angle of alpha. This is the free body diagram, as we said. So, for these two elements we have the equation of motion, and for this element, that is the curved portion, to analyze the motion of the part in the curved section B C of the feed track, it is necessary to consider an element of length r d theta, which is this one, on a portion of the track that is inclined at an angle theta to the horizontal. So, this is the theta angle, and here we are taking one small section, that is r d theta of the length. D theta is this angle, okay, and r is the radius of this curved portion. So, r into d theta will be the length. Now, here for the section that we have taken, that element, and in this element, let us say the forces which are acting, we have the d theta here. So, d theta, then we have divided into d theta by 2, d theta by 2 in the middle, and here this is the normal force which is acting, let us say this is N 1. So, therefore, because of this normal force, there is a friction force which is mu d into N 1, okay, and this is the mass of the part acting as m 1 g, and the r d theta is the length, as we said. And here we will have two forces, that is F and F plus d f, okay, on this element, small element. So, they will be acting at an angle of d theta by 2, as we said here, and here it is F and incremental of that. So, F plus d f. Now, in this case, a force F resists the motion of the element, that is the F, and a force F plus d f tends to accelerate the element, okay, because we have selected that element. These forces have a small component F d theta that increases the reaction between the parts and the track, and consequently increases the frictional resistance. Okay. Now, the equilibrium equation of force, once again I have drawn this here, the same diagram as in here. So, from here you can see the equilibrium equation of forces in the radial direction n, let us say in this direction. Okay. In here what we have is the n 1 itself, n 1, and this is opposed by m 1 g r d theta and the cos theta, which will be a component of this, meaning that in here if you say that these components, I mean this force will have two components, one is in the direction of the n and another is in the vertical direction of the vertical to n. So, along the direction of n, this will be cos theta, and vertical to the n will be the sin theta, which will be coming when we will take it in this direction. In the direction of n 1, we will have n 1, and this force component will be in this direction. Okay. This will be m 1 g r d theta and the cos theta, cos theta. So, since it is opposite to n, so this will be m1 g cos theta d theta plus f d theta. F d theta is coming from here, that is, this is the f and this is the f and this is the f plus df. So, if we ignore really df and the d theta, that is a very small value. So, then we will have that f d theta by 2 plus f d theta by 2. So, this will be f d theta, that is why you have taken, and this direction will be along the direction of the m1 g r d theta cos theta. So, therefore, these two signs are the same, n1 sign is opposite. So, the equilibrium equation will be this, that is n1 minus m1 g r d cos theta minus f d theta, because of these two, because here the component will be coming in this direction. The equation of motion in the tangential direction, let us say in this direction perpendicular to n1, this will be the friction force mu d n1, that is 1. Then we will have the f cancelling and we have the df. So, the df, this is the first element. Then we have the m1 g r d theta and here it will be sin theta. So, this will be in the opposite direction to mu d n1. So, therefore, this is plus and this is minus mu d n1. This is equal to m1 r d theta and the acceleration. A is the initial acceleration of parts in the track. Okay. So, this is understood that we are taking the equilibrium equation, force equation in the direction of the n1 and in the direction vertical to the n1. Rearranging the terms, the following first order linear differential equation with the constant coefficient can be obtained. So, we are rearranging these two, this one and we are finding that this is df by d theta, the minus mu d and the f is equal to m1 r acceleration plus mu d g cos theta minus g sin theta. Okay. The general solution of this equation, if you take this, it will be something like this, all right. So, this is the general solution, this is given in the mathematics, the mathematician can find out. So, this equation relates the acceleration of the line of parts along the curved and horizontal sections of the track when a force F is applied to the end of the line located at an angle of theta. Now, for us this is not so important, what is important is the final equation that we will be getting, the final solution that we will be getting, what are the components that will be involved in that. So, there are two applicable boundary conditions, theta is equal to 0, then f becomes f1. Okay. You can see this from here, theta is equal to 0. So, f is becoming the f1 which is coming here, all right, which is coming here. Then the another condition is that when the theta is alpha, then f is equal to f2. This is this, theta is equal to alpha, which is the angle here, this alpha, then this f is equal to f2. So, we are using the boundary condition, the first boundary condition which is theta is equal to 0, where the f will be equal to f1, we can find out this equation, all right, from here. And the second one, using the second boundary condition and solving the equation earlier that was given for A by G, we can find out is equal to L2 by R this minus L1 by R mu d e to the power mu d alpha plus so on and so forth. So, as I said that we are actually interested in the final solution, the components. This equation shows the relationship between the non-dimensional acceleration A by G, okay, of the entire line of parts and the design parameters L2 by R, L1 by R, alpha and mu d. This is more important for us. Okay. By the way, this A by G we actually said this is A n by G n, this is the same thing, please mind it. Okay. This is equivalent. So, finally what we are getting is the non-dimensional track acceleration and we are getting different kind of parameters here. So, these parameters actually tell us that An by Gn, which is the non-dimensional track acceleration, this can be written as a function of mu d, function of L1 by r. L1 is the length of the straight path, r is the radius of the curved path, then alpha, which is the inclination angle of the straight path inclined to the horizontal with an angle alpha, and L2 by r. Okay. So, these are the design parameters that is important, and then when you have the track, if you are designing the track, so that you can find out what will be the An by Gn, that is the normal track acceleration, dimensionless normal track acceleration. So, the time Tp for one part to move into the workhead, that can be found out from the kinematic expression of Tp equal to 2L by A root over. So, this we have seen earlier in the case of the vertical delivery feed track, that this is the Tp, that is the time taken. So, here we have the acceleration which can be selected, the one that we are getting from here. So, this is for horizontal delivery feed track, which once again I will say that this is not a very big deal, that we are just taking the free body diagram of the straight path, of the straight incline and the curved portion, and in each of these we are finding out what should be the equation of motion, and then we are solving them together to get an equation which will give you the general solution of the equation, and from here we are finding out what are the boundary conditions, and from the boundary condition we are finding out the An by Gn, that is the normal track acceleration. And we see that the normal track acceleration is a function of dynamic coefficient of friction, L1 by r, alpha, and the L2 by r. So, this is more important for us to find out that how they are related. Let us discuss one thing which is interesting, which is called the on-off sensor in the feed track. See, what happens is, when automatic feeding devices are used on the automatic assembly machines, the mean feed rate is usually set at a higher rate, okay, than the assembly rate, to ensure a continuous supply of parts at the workheads. I told you this thing earlier also, that workheads should not starve, because that will then affect the other adjacent workheads. Mind it that in a flow line, as I said, I will remind you, the workheads are subsequently arranged, and the material handling device passing on one subassembly from one workhead to another workhead. So, if we cannot feed the part to the at the right time, then that machine will suffer, will starve, and the other machines will suffer because of that. Okay. So, therefore, not to do that, not to start the machine, we actually put the F into Vm of the ball feeder little higher. Okay. Under these circumstances, the feed tracks become full and parts back up to the feeder. Okay. For vibratory ball feeders, however, this method is not always satisfactory. With these feeders, the parts in the line in the feed track are usually prevented by a pressure brake. We have seen the pressure brake, you remember. This is that the one that prevents the certain parts of certain orientation to go through, because the track is narrowed. Okay. So, that pressure brake from interfering with the orienting devices mounted on the ball feeder track. If a part filters past the orienting devices and arrives at the pressure brake when the delivery chute is full, it is rejected back. So, what we mean is that suppose the conveying velocity, as we said, that it is set little higher. So, because of that, the parts which are coming to the assembly machine, the assembly machine is still not ready to take it, because our feed rate is higher. So, in that case, the parts will actually fall to the bottom of the ball feeder, because the feed track is filled up. So, that part cannot go to the feed track even. So, that will create the excessive wear both the bowl and the parts because of the recirculation. So, once again that in that case what happens, the pressure brake is there, pressure brake is narrowing the track, and if the part feed track is filled up, because the ball feeder F into Vm conveying velocity has been set little more than the parts number of parts machine can accept, then the parts will fall on the at the bottom of the bowl. If the part is falling at the bottom of the bowl, it will again recirculate and then it will get into the friction with the other parts. It will create the wear and tear of the parts and of the ball as well. So, let us see the on off sensor how it works to prevent this problem, okay, that we will discuss in the next class. Thank you very much.